Even the little remote control you use, the one you lose in the couch cushions. What if I told you that a single, how pretty much all those devices actually work? Today, we're taking a deep dive into the Planck-Einstein relation. Now, I know, sounds super scientific, right? But it's actually this unsung hero hiding in plain sight, powering in this vast ecosystem of modern consumer tech, our mission. Let's unpack how the century-old formula became the invisible blueprint for, well, quite literally, the light in your life.
Yeah, and what's truly fascinating here is that, this equation isn't just history. It's not just a museum piece. It really is the core design rule, as you said. It dictates the function, the form, even the economic feasibility of countless devices we rely on every single day. Understanding E isn't just about appreciating the science behind it. It's actually essential for getting a grip on our current technological landscape. And even for charting where future innovation might take us, it utterly transformed how we understand light. Basically turned the entire electromagnetic spectrum into this functional hierarchy of energy, which then became, a prescriptive design principle for engineers all over the world.
Okay, let's start at the beginning then. Let's journey back to the late 19th century. Classical physics was, well, it's hitting some serious walls. Scientists were grappling with something called the ultraviolet catastrophe. So imagine this theoretical black body radiating energy. Classical theory predicted it would emit infinite energy in the UV range. Infinite, which was obviously wrong. Measurements clearly showed there was a limit. It was a real crisis. Theory just smashing against reality.
Exactly. Yeah, that discrepancy was a huge problem, a glaring failure. Then, in 1900, Max Planck steps in. He proposed this really radical, almost reluctant solution. He suggested energy isn't, smooth and continuous. It comes in these discrete, indivisible packets he called quanta. And his formula, E high, introduced H Planck's constant, which we now understand is this fundamental scaling factor. It connects light's vibration, its frequency, to its energy. But Planck himself, he initially saw this quantization as more of a mathematical trick, almost an act of desperation, just to make the math fit the data. He was kind of a counter-revolutionary in his own mind.
A mathematical trick. Wild. But then, okay, here's where it gets really interesting. 1905, Albert Einstein. He makes this critical conceptual leap. He didn't think Planck's idea was just about how energy was emitted. He thought light itself was made of these discrete packets, which we later called photons. So if Planck was kind of hesitant, what gave Einstein that, intellectual courage to just go all in and say light is particles?
That is a great question. Einstein was, he was bold. He took Planck's sort of mathematical fudge factor and declared it physical reality. And then he used this revolutionary idea to finally explain another big puzzle, the photoelectric effect. You see, when light hits metal, sometimes electrons get ejected. But weirdly, their energy depended on the light's frequency, its color, not its brightness, its intensity. And below a certain threshold frequency, no electrons came out at all. Didn't matter how bright the light was. Einstein explained it perfectly. Each photon, with its specific energy packet, E, transfers all its energy to a single electron. If that photon had enough energy, meaning if its frequency was high enough, boom, it could knock an electron loose. More intense light just meant more photons hitting the metal, so you got more electrons, but not more energetic ones. It was a profound insight, really profound.
Wow, that's truly mind-bending. So Einstein's work basically cemented E high as the statement on a photon's energy, and confirmed light is both a wave and a particle. We often see it written as EC2, right, where C is the speed of light and Leland is the wavelength. What's the key takeaway from that version for us?
Oh, yeah, easier. That form is super useful because it really highlights the inverse relationship, energy versus wavelength. So think of Planck's constant, ET, as that universal conversion factor. It links how fast a photon jiggles, its frequency, to how much punch it packs, its energy. This means essentially if you want photons with more energy, photons that can, do more work, make bigger changes, you need light with shorter wavelengths. Short waves, high energy. Long waves, low energy. It's this simple inverse relationship that unlocks, almost everything in modern optics, from your TV remote to UV sterilizers.
Okay, so what does this all mean for you listening right now? How does this translate into daily experience? It means the whole electromagnetic spectrum, from those long, lazy radio waves carrying music to the super short, energetic X-rays doctors use. It's fundamentally an energy spectrum. The energy carried by each individual photon dictates what that light does when it hits something. It's not just abstract physics. It's a precise, prescriptive design principle for engineers. Think about it. Low-energy photons, like infrared or microwaves, they typically just have enough energy to make molecules wiggle or rotate. That's your microwave oven heating food, or maybe a heat lamp warming you up. Visible light photons. They've got just the right energy kick to cause electrons to jump between levels in atoms. That's how our eyes see, how plants do photosynthesis. But then you get to the high energy end, like ultraviolet or X-rays. Those photons pack enough punch to actually break chemical bonds, ionize atoms. That's why UV light can sterilize things. But it's also why it can be hazardous to us, this transformation of the spectrum into a functional hierarchy of energy packets. That's really the key to understanding almost all modern technology. We've got the fundamental idea down. EZ tells us the energy of a light particle. So how does this actually translate into something tangible, like the light bulbs in our homes or the screens we stare at all day? What's maybe the simplest way E starts making visible light for us?
The simplest everyday example is probably the LED, the light-emitting diode. Think of semiconductors as materials that are very carefully engineered. They have specific energy levels where electrons are allowed to hang out. When an electron drops from a higher energy level, like falling off a step, down to a lower one, it has to release that extra energy. And it does that by spitting out a photon, a packet of light. Now, here's the crucial A part. The energy difference between those two levels, that step height, directly dictates the frequency and therefore the color of that emitted photon. So engineers pick specific materials like gallium arsenide phosphide because its energy gap makes red or yellow light. For green and blue, they use something different, like indium gallium nitride. And actually, the development of an efficient blue LED, that was a massive scientific breakthrough. Earned a Nobel Prize, in fact. Precisely because getting blue light was so hard, and it was the missing piece needed for white light and full-color displays.
That makes sense. The material itself sets the energy gap, which sets the color. Simple enough. But what if you want even more precise colors, really fine-tuned things, like for a fancy high-def TV? That's where quantum dot displays, QLEDs, come in, right? Taking this whole principle like to the next level.
Exactly. QLEDs are where quantum confinement gets really fascinating. So QLEDs usually start with a blue LED backlight, yeah. But the real magic happens in this thin film layered on top. It's filled with these tiny semiconductor nanocrystals called quantum dots. And when I say tiny, I mean just a few nanometers across. Like unimaginably small. Because these dots are so incredibly small, the electrons inside them are sort of squeezed, they're confined, and this confinement actually changes the allowed energy levels within the dot. It makes the effective energy gap size dependent, so you get these really small quantum dots, maybe 2 or 3 nanometers wide. They squeeze the electrons more, force them into higher energy levels. This means a larger effective energy gap, and so they re-emit higher energy light blue or green. Then you have slightly larger dots, say 5 or 6 nanometers. Less confinement, smaller energy gap. So they re-emit lower energy light orange or red. It's pretty cool. And what's amazing for manufacturing is you can use the same base material, something like cadmium selenide, and produce a whole rainbow of colors. How? Simply by controlling the size of the nanoparticles during synthesis. You tweak the reaction time, the temperature, and you get different sizes with atomic precision. It basically shifts color creation away from complex material chemistry and more towards precision process control. All thanks to this size-dependent E-high relationship right down at the quantum scale.
That's incredible. The size of the particle literally determines its color. Wow. So these are like tiny, perfectly tuned light-emitting machines, and E is basically the instruction manual telling them what color to be. Okay, so moving from just general lighting to a really focused beam, something that can read data or even perform surgery. The laser. This is where you get, as you said, armies of identical photons all marching in perfect lockstep. How does E-high manage that kind of precision?
Right, the laser. The key principle here is something called stimulated emission. It's actually another idea Albert Einstein proposed way back in 1917. So without getting too deep into the physics weeds of population inversion and metastable states, imagine you have atoms in your laser material and you've pumped them full of energy. They're sitting in this excited state, like wound up springs, just waiting for a very specific nudge. Now, a random photon happens to wander by, but crucially, this photon has exactly the right amount of energy, corresponding to the energy difference the excited atom wants to release. That photon gives the atom the perfect cue, and when it does, the excited atom releases its energy by emitting an identical photon. Same energy, same frequency, same direction, same phase. A perfect quantum copy. This kicks off a chain reaction. 1 photon triggers 2, 2 trigger 4, and so on. It's like a quantum copy machine, amplifying the light incredibly quickly. And the result is that intense, perfectly coherent laser beam, the energy of every single photon in that beam, rigidly determined by that specific energy transition within the laser material, all thanks to E.
A quantum copy machine, I like that. Okay, so we know how these precise photons get made. Let's see them in action storing information. Think about optical discs, CDs, then DVDs, then Blu-ray. I definitely remember the jump in quality and storage with each one. How did EHI drive that whole evolution?
Oh yeah, that's a fantastic real-world example of basically just marching right up the energy spectrum exactly as dictated by Iggy. The main challenge for getting more data onto those disks was something called the diffraction limit. Basically, how small could the little data pits etched onto the disk be? And the size of the spot the laser could focus down to read those pits. That was directly proportional to the wavelength of the laser light itself. So to pack more data, you needed smaller pits, which meant you needed a smaller laser spot, which meant you needed a shorter wavelength. It's a direct consequence of Iggy. So we saw this clear progression. CDs used a 780 nanometer infrared laser, relatively long wavelength, lower energy, it got you about 700 megabytes. DVDs. They shifted to a 650 nanometer red laser, shorter wavelength, higher energy, bumped capacity up to around 4.7 gigabytes, and then came Blu-ray. That was a big jump. It uses a 405 nanometer blue-violet laser, significantly shorter wavelength, much higher energy photons. This allowed for an incredibly tiny spot size, just 580 nanometers, which is how they crammed 25 gigabytes onto a single layer. Honestly, the entire multi-billion-dollar R&D effort behind Blu-ray, it was almost entirely focused on the massive engineering challenge of creating reliable, mass-producible gallium nitride semiconductor laser diodes that could consistently pump out photons at that specific high-energy, short-wavelength point. It's EHI driving huge technological shifts.
It's amazing when you think about it like that. Billions spent just to climb higher on that E-hider. But okay, what about something way simpler, like the TV remote you mentioned earlier? You use it every day. That also relies on the E-high, but it's working in a totally different part of the spectrum, isn't it?
Absolutely. Completely different strategy there. Your TV remote uses an infrared LED, an IR LED. Typically, it emits light around 940 nanometers. Now, according to EHI, these photons have very low energy, only about 1.32 electron volts. That energy is well below the threshold for human vision, which is why you can't see the beam when you press a button, though sometimes your phone camera can pick it up, which is a neat trick. So the remote just sends simple binary commands on-off pulses of this invisible IR light. And your TV or whatever device has a little photo detector specifically tuned to be sensitive to that 940 nanometer wavelength. What's clever here is the engineering trade-off they made, guided by EHI. That really low photon energy means these IR LEDs are incredibly power efficient. Your remote can run for ages on tiny batteries. They're cheap to make. And crucially, the signal doesn't usually go through walls, so it stays contained in one room. You're not accidentally changing your neighbor's channel. It's a perfect compromise. Effective, practical, cheap, all by choosing the right low-energy photon.
Right, a perfect compromise. Okay, so from these like discrete signals zipping across the living room, let's go global. Let's talk about the backbone of our entire digital world, fiber-optic communication. This powers the internet. And here, EHI is used in a really fascinating way, not to maximize energy, but actually to minimize how the light interacts with the glass fiber it's traveling through. How does that work?
Yeah, this is a really elegant application. It's all about avoiding interference and signal loss. So you convert data into pulses of light, usually from a laser or maybe an LED, and send it down these incredibly pure glass fibers, right? The big challenges are signal loss attenuation and the signal getting smeared out dispersion. Both happen because the photons inevitably interact with the atoms in the glass fiber. But material scientists discovered these special window-specific wavelengths where the glass is exceptionally transparent, particularly in the infrared range, around 1310 nanometers and 1550 nanometers. At these exact wavelengths, the photon energies, dictated by E, just happen not to align well with the natural vibrational or electronic energy levels of the silica glass molecules. The photons are kind of out of tune with the glass, so engineers very deliberately choose lasers precisely tuned to emit light at these optimal low-loss wavelengths. It's all about minimizing interaction, maximizing transmission efficiency, allows data signals to travel thousands of kilometers under oceans and continents with remarkably little degradation. It's brilliant, really, using quantum mechanics to avoid interactions.
It really is profound. The same basic rule governs the immense energy of an X-ray, the gentle, invisible pulse of your remote, and how the entire internet works by essentially being out of tune with the medium. Okay, let's switch gears a bit. How does light itself become power, or how does it create the images you capture, like on your phone? Solar panels seem like the obvious place to start.
Absolutely. Solar panels or photovoltaic cells work via the photovoltaic effect. Sunlight hits the semiconductor material, usually silicon, and generates electricity. But sunlight isn't just one color, it's a whole spectrum of photons with a wide range of energies. And here, EI, combined with the properties of the semiconductor, acts as the ultimate gatekeeper for efficiency. Silicon, for example, has what's called a band gap of about 1.12 electron volts. This is the minimum energy needed to knock an electron loose and create current. So here's the crucial trade-off, the efficiency limit. Any photon from the sun with energy less than that 1.12 eV band gap, it just doesn't have enough energy, it passes right through the silicon. Poof, energy lost. Okay, but what about photons with energy greater than the band gap? They are absorbed, they do knock an electron loose. But the extra energy, the amount above the 1.12 eV band gap, so E photon minus E gap, isn't converted into useful electricity. It gets wasted almost instantly as heat. It's a process called thermalization. This fundamental limitation, directly governed by E high and the material's band gap, leads to something called the Shockley-Queisser limit. It's a theoretical maximum efficiency for a single junction solar cell like silicon, somewhere around 33%. It's a quantum mechanical bottleneck we're constantly trying to engineer our way around.
A quantum bottleneck, limiting how much solar power we can get. Fascinating. Okay, so from powering homes to capturing memories, you mentioned digital cameras. They work on similar quantum principles, right? Every photo you take is pixel. At billions of tiny quantum events.
That's precisely right. Think of your digital camera sensor, whether it's a CCD or CMOS sensor, as this grid, this mosaic made of millions of tiny individual light catchers called pixels. Each pixel contains a photodiode. The process starts once again with E high. An incoming photon from the scene you're shooting hits the silicon sensor. If that photon has an energy that's greater than silicon's band gap, that same 1.12 eV, it gets absorbed. This absorption does the same thing as in a solar cell. It creates an electron-hole pair, essentially liberating a free electron, a photoelectron. Each pixel, each photosite, acts like a tiny bucket, collecting these photoelectrons. The brighter the light hitting that pixel, the more photons arrive, the more electrons are collected in the bucket. Then the camera measures the charge accumulated in each bucket and converts that into a digital brightness value for that pixel. To get color, there's usually a filter mosaic, like a Bayer filter, over the pixels, letting only red, green, or blue light through to specific pixels. But fundamentally, yes, a digital photograph is a direct quantitative map of billions upon billions of individual quantum absorption events, all governed by whether I was enough to clear the band gap hurdle.
So every selfie is basically applied quantum mechanics. Amazing. Now, not all applications of light are about creating things or sending signals. Sometimes you want to use light's energy for, let's say, destruction, but in a good way, like UV sanitization. You see these in water purifiers, sometimes air filters. How does E-Chi play the role of germ killer there?
Right, UV germicidal irradiation, or UVGI. This typically uses light in the UVC part of the spectrum, which is wavelengths between about 100 and 280 nanometers. The peak effectiveness for killing germs is usually around 254 to 265 nanometers. And the key reason why that specific wavelength range works so well, it's because photons at those wavelengths are very, very strongly absorbed by the nucleic acids, the DNA and RNA inside microorganisms like bacteria and viruses. According to E-high, UVC photons are highly energetic. A 254 nanometer photon, for instance, carries about 4.88 electron volts of energy. That's a pretty hefty punch at the molecular level. That energy is more than sufficient to be absorbed directly by the molecular bonds within the DNA or RNA structure. This absorption often causes covalent bonds to form between adjacent bases in the genetic code, particularly creating things called thymine dimers. This structural damage creates a sort of kink or lesion in the DNA helix. That kink physically prevents the DNA from replicating correctly, so the pathogen can't reproduce. It's effectively inactivated, or you could say killed from a reproductive standpoint. It's really a kind of Goldilocks zone of energy dictated by E-high. The photons need to be energetic enough to reliably break those crucial molecular bonds needed for microbial life, but still be, producible and containable within a safe and affordable consumer device using things like mercury lamps or specialized LEDs.
A quantum Goldilocks zone for germ killing. That's a great way to put it. Okay, so everything we've talked about so far, LEDs, lasers, solar cells, UVs, it mostly relies on what people sometimes call the first quantum revolution, basically using the collective quantum properties of billions of atoms and materials. But now we're hearing a lot about the second quantum revolution. This is supposed to be about manipulating individual quantum states, things like superposition and entanglement. So where does our old friend E-high fit into this new, maybe even weirder quantum future? Does it still matter?
Oh, absolutely, it still matters. EI remains completely foundational because even when you're manipulating individual quantum states, you often need photons, light with precisely controlled energy to do that manipulation or to read out the state. So EI is still the rulebook for the energy of those photons. But yes, the focus shifts. In the second quantum revolution, we're moving beyond just controlling the energy defined by EI and trying to leverage those stranger quantum properties like superposition, where a particle can be in multiple states at once, and entanglement, where particles are linked in spooky ways. We're using these for totally new kinds of information processing and sensing. So think about future solar, for example. People are working on quantum dot solar cells. They use those size-tunable quantum dots we talked about to absorb a much broader range of solar spectrum energies. And some can even do something called multiple exciton generation, or MEG. That's where one single high-energy photon can actually create more than one electron-hole pair, potentially smashing right through that old Shockley-Queisser limit. There are also perovskite solar cells, which have tunable properties and are hitting amazing efficiencies, especially when paired with silicon. Or look at quantum computing. The basic unit, the qubit, exists in a superposition of 0 and 1. E still governs the energy of the microwave pulses or laser beams used to manipulate and read these qubits, but the goal is vastly more powerful computation. We're even seeing early commercial tech like MRAM magnetic RAM that uses quantum spin. Then there's quantum communication, using entanglement to create fundamentally secure communication channels. You hear about quantum key distribution, QKD protocols, potentially built into future phones for unhackable communication. And quantum sensing, using quantum effects for incredible sensitivity. Imagine quantum dot biosensors in your wearable, giving real-time health data, or advanced navigation that doesn't need GPS. Even things like SWARE shortwave infrared sensors based on quantum principles, potentially bringing low-cost night vision to consumer devices. EHE sets the energy scale, but the game is now about controlling the full quantum state.
Right. So the second quantum revolution doesn't replace EE, but builds on it. It means our devices won't just be built using quantum mechanics passively like an LED is. They'll actively compute and communicate and sense using individual quantum phenomena. It really feels like this journey of mastery, doesn't it? From first mastering the energy level, getting the right E for LEDs and lasers, then mastering physical dimension, tuning the size of quantum dots, and now moving towards mastering the full quantum state itself. It's a whole new level.
Exactly. And if we try to connect this all back to the bigger picture, the Planck-Einstein relation, E-high, it's just so much more than some abstract formula you memorize in physics class. It is, and this isn't really an exaggeration, it's the single most important design principle governing how light and matter interact in pretty much all of consumer technology.
Yeah, absolutely. We've seen today how it determines the exact color of your TV screen, the data capacity of your Blu-ray disc, the fundamental efficiency limit of your solar panel, the germ-killing power of a UV purifier, even how the internet signal travels across the globe through fibers. It's everywhere. It's truly firmly in your shopping cart, even if you never realized it. So what does this all mean for you? For the everyday consumer, it just means that this quantum world, which maybe seemed abstract or theoretical, maybe something debated in labs a century ago, it's now the absolute bedrock of our modern convenience. And it's clearly the foundation for whatever amazing innovations are coming next.
Which, raises an important question, doesn't it? What other fundamental scientific principles, ones that seem maybe just as abstract as Ewing-West did, are quietly orchestrating the unseen magic in your daily life right now? And maybe more excitingly, how much more of this quantum world, the first revolution and especially the second, is going to emerge from the research labs and end up right there in your hands in the coming years? It's kind of a provocative thought to leave you with. The deeper you dive into this quantum realm, the more you start to realize that the world all around you is constantly whispering secrets. You just need to learn the language to listen. What will you discover next about the quantum mechanics woven into your everyday experience?